the first synthesis of the sterically encumbered adamantoid phosphazane P4-NT-butyl-6, enabled by mechanochemistry. The theme of this week's session is really to highlight a new type of catalysis that I had never considered before. And if you're anything like me, this will probably seem like an out-of-this-world idea to you. Mechanochemical activation. I'm going to present to you 4 papers this week that highlight the usefulness of this technique. In one case, they create an adamantoid phosphorus nitrogen framework. In the second, using ball milling, they complete the Biginelli reaction, yielding substituted dihydropyrimidones. Thirdly, heteroacenes of long chain length are created by mechanochemical synthesis. Fourthly, the Ugi and Passerini reactions are carried out in a solvent-free manner using high-speed ball milling. To make things clear, let me explain that adamantoid phosphazanes, that is phosphorus nitrogen backbone compounds, have not successfully been made to date. There are 2 main forms of phosphazanes. One of them is a type of bispiro. It's basically like a sulfur 8 ring with a bridging 1 carbon chain. The second type is an adamantoid form. In this case, they produced a phosphorus nitrogen backbone compound in which the nitrogens are covalently coupled to bulky carbon-based groups, T-butyl. The author's first goal was the conversion of a sort of quasi-adamantoid form into its adamantoid isomer using ball milling. Now, ball milling is where in a small rolling mill, many tiny metal beads are used to crush powdered chemicals, and it's thought that the high temperatures created by collisions could act as a form of catalysis. This can be done by solvent-free methods or by including small amounts of a liquid solvent. In their first attempt, they used toluene, or THF, in a ball mill at an eta parameter of 1 microliter solvent per mg of solid reactant. They succeeded in converting the pseudo-adamantoid isomer into the adamantoid form. But don't take my word for it. Check out these 2 phosphorus NMRs. The upper one is the starting material, the lower one being the adamantoid form. I would say, judging by the fact that the phosphorus hydrogen has changed in its chemical environment from 146 to 47 chemical shifts, this would suggest complete conversion of the starting material into its product. Pardon me, the first thing they tried was actually using an isopropyl substituent. The second reaction they tried and also completed, and which this NMR is a spectrum of, was using T-butyl. What happened was after the ball milling reaction, they recrystallized the compound number 4 from toluene. After that, they took a small NMR spectrum. Interestingly, the authors reported that including high quantities of salt, in this case lithium chloride, to the ball mill drastically increased the efficiency of catalysis, although there was a reduction in catalysis above 20% salt. Evidently, when you overload the reaction with salt, there could be less efficient mechanical impact on the reactant. As well, the reaction mixture would be diluted. In the last bit of their paper, the authors performed some theoretical calculations and determined, in fact, that the leading mechanism, a twist mechanism that would account for the conversion of this pseudo-adamantoid structure into an adamantoid one. In this postulated twist mechanism, it's kind of difficult to draw, but I can do it more efficiently with hands. In this mechanism, two bonds would break and two bonds would be formed at the same time. Instead, the authors propose that it proceeds in a two-step process through an intermediate, which my teacher told me in mechanism, there's always an intermediate unless the intermediate cannot exist. Nature likes to proceed through intermediates. In summary, through the creation of short-lived hot spots or high-energy amorphous phases, continuously agitated ball mill reaction environments should be considered over the typical round-bottom flask organic solvents. You know, this whole thing is really hot these days. Green chemistry, but not just, I find this a prime example of green chemistry. We're not just recycling solvents from our columns, okay? We're not just performing our reactions in water. We're reimagining. And this is probably a quite biomimetic, in a way, type of reaction, because what you're doing is creating fortuitous high-energy environments, which would be similar to the random chance that happens in nature in order to create complex compounds. In this case, it was used to great effect to purify a compound that's not usually stable in solution, but since it was performed with very little in a solvent-free approach, the solid product is stable. So in fact, it's our flawed paradigm of using solvents for everything that actually destroys a lot of fragile compounds. Next, green chemistry. What's hot in green chemistry? Solvent-free reactions. What's hotter than green chemistry? One-pot reactions. What's the hottest part of one-pot reactions? Multi-component synthesis. Solvent-free ball milling Biginelli reaction by subcomponent synthesis. European Journal of Organic Chemistry. Very highly regarded. Short communication. Let me take you through the steps. The reaction initiation uses oxone, which is a heavy oxidizing agent, and the radical scavenger tempo. It's a nitroso radical compound. In 30 minutes in a ball mill, a primary alcohol can be converted into an aldehyde, which is also generally not stable at room temperature, but there you go. Obviously, the aldehyde would be used in situ. In this case, it reacts with an urea and a ketone to produce something that looks very similar. This is why I said biomimetic. Something that looks very similar to a pyrimidine. It's in fact a pyrimidone, a dihydropyrimidone. Anyway, 3-component ring formation biomimetic. Well, it's in this paper that the initial reaction conditions were a bit tricky. They tried various oxidizing agents in order to prepare the aldehyde, so it's by no means that aldehydes are easy to prepare, but with the proper mix of oxone with the radical scavenger tempo, they were able to basically perfect their yield and bring down the time required for the reaction as well. Off the bat, they could scarcely get their reagents formed. They had a 94% yield of their aldehyde within 4 hours, but they could not get the multi-component reaction to work. Finally, by the end of this, with the right conditions and the right lengths of time, the yields of the 3-component product go as high as 95%. Not only that, they were able to observe regioselective synthesis by using an imbalanced urea, an asymmetrical urea that was N-methylated on one of the groups. With this, they managed to produce 5 different compounds, which seemed to have a lot of therapeutic promise. I don't know, I'd put them in my drug library. Alright, I know what you're saying. I'll believe it when I see it, right? Here's some NMR spectra of the aldehyde. top one would be using their pretty flawed oxidation method where they used succinimide and didn't get a very pure product. But by the end of optimizing their reaction conditions with tempo and their oxone reducing agent, they were basically able to get a pure product of the aldehyde. Alright, so again, here's just a little schema of the final of the reaction framework. So you start off with an aldehyde, you basically add to that in a three-component reaction with a ketone and a urea, and it has this ring formation. So you're going to form a pyrimidone that's substituted with an arrow group. Please go check out this paper. It was published in Year JOC. Prasad Kumar Sahu, Anima Bose, and Prasenjit Mal. Some very interesting science coming out of India with this solvent-free reaction paradigm. Check it out. Alright, the next paper concerns an interesting class of compounds, the acenes, which you all know are just a bunch of benzene rings stacked in a long line. In this case, they examine the formation of N-heteroacenes, which would be the linkage of two large acenes, basically, by reacting a diketone with a diamine on the other side, efficiently just stitching these two parts of the molecule together. So here, amine and diketone, you stitch them together and you get a ring formed. In that way, you can kind of add on different parts of the acene onto a longer chain. As you can see, this method lends itself quite well to either symmetrical or asymmetrical reactions. So what do? We try to synthesize them by ball milling. Why not? This is by the same authors as the last one, Prasenjit Mal. Alright, so what they're attempting is a solvent-free cyclocondensation reaction, a condensation between an amine and a ketone. And what do? Basically, they use p-toluene sulfonate as the catalyst, ball mill, ambient temperature. After the reaction, they wash a little bit of the product out of the flask, run an NMR. Look, the commonly used methods to synthesize pyrazine-containing heteroacenes use ethanol acetic acid or acetic acid under reflux in the presence of a strong oxidant 2-iodoxybenzoate. See, the reaction conditions are hazardous, time-consuming, and they have poor yield. Okay, you guys are experienced chemists, so you'll know that photophysical study is important for this class of compounds. They're large, they're conjugated. You're not going to run an IR on this kind of thing, okay? You do a UV-vis absorption spectrum because they're active in the normal range of light. They're fluorophores. So they present some interesting spectra and quantum yields for these compounds. I'm not exactly familiar with any of them, so I couldn't tell you if it was right or not. Basically, what they did was when they took a crystallographic investigation of these compounds, they say this: the molecular structure is not very interesting by itself. However, pi stacking interactions in the crystal could be quite interesting to see. Once you get the unit cell, you'll be able to see how do these molecules crystallize. Well, what they saw was obviously they've got some pi-pi system interactions, but they also have CH-pi, well, I don't know if it's really an interaction, but the methyl groups on the end kind of stack right in the middle of a benzene ring. Their crystals were further stabilized by the inclusion of trifluoroacetate, which seems to kind of buffer up those amine groups too. Alright guys, Prasenjit Mal, go search him on PubMed right away. Alright my students, final paper, Ugi reaction, 3-component, and Passerini reaction, 4-component. You guessed it, it's mechanico-chemical. The Ugi reaction was invented in '59, and it's a 3-component reaction including a ketone, an amine, an isocyanide, and a carboxylic acid. Ugi reaction was first reported in '59. It's a three-component reaction to form a bisamide. Interestingly, it's an uncatalyzed reaction. It's produced normally just in an organic solvent or in water. And interestingly, one important product of the Ugi reaction is Crixivan, an HIV drug. Several studies concerning the solvent-free syntheses of Ugi and Passerini adducts have been reported recently under magnetic stirring, ultrasound, microwave-assisted, or by manual grinding. In this study, a mixer mill MM200 ball mill was used. In this case, the physical state of the starting material, benzaldehyde, propargylamine, and tert-butyl isocyanide, was sort of a brownish crude oil. The authors used silica gel as an additive in the ball mill because they found that the reactants adhered well to the silica gel, potentially increasing the reaction rate. In fact, they found that they had better results using liquid-assisted grinding. So using silica gel, their crude oil, and a bit of methanol at an eta factor of 0.44 microliter per milligram. However, this may indicate that the Ugi reaction is not ideal for mechanical chemical synthesis because maybe it's better in solvent. Contrary to the case of the phosphazane we saw earlier, this reaction worked better with liquid assisting grinding. However, the authors were very clever, and to compare the efficiency of the solvent-free protocol, they did their own internal control by performing the reaction under previously reported solution conditions, methanol, indium trichloride, at 50 degrees for 2 hours. And basically they only got 30% yield, which is far lower than what they got from the milling process, which was more like double that. In the case of the four-component Passerini reaction, they obtained comparable yields to those obtained by solvent-based conditions. However, it's important to stress that the solvent-free approach drastically minimizes the energy required in order to conduct this reaction. So, this paper, Ugi and Passerini adducts under mechanochemical activation, was brought to you by two scientists from Mexico, Luis Polindara Garcia and Eusebio Juaristi. It's good to see some Química Latinoamericana. Please check out all of the above papers that we checked out, Prasenjit Mal, Eusebio Juaristi, and this group from Spain, Antonio Echavarren, synthesizing bovalines. That's all for this week, folks. Thanks for tuning in, and keep studying.